Good morning. John Gilkison here. It's Monday, September 20th, um, 2021. And I've been wanting to shoot a video on energy to mass conversions for electric vehicles for a few days. Uh, this whole subject matter started out whimsically enough. I was talking to a friend on the phone last Wednesday, and we were talking about the fact that energy and matter are equivalent. So when I drove my electric car, it lost mass, and it it's just a joke. But I'm speculating that I got better energy efficiency when the battery was empty because of the lost mass. And of course, the loss in mass is so minuscule. It's just a joke. But Scaris is just wondering what the exact loss of mass would be, and I just needed to work it out. So I did, and it involves the Einstein formula E equals mc squared. Um, and what I figured out was I have a 2019 Chevrolet Bolt. Right there it is. And it has a 60 kilowatt hour battery pack. And if I charged it up 100%, I would more than likely only drive it down to about 10% of battery before I'd charge it again. And this means that I would only use 54 kilowatt hours. So we needed to know the mass of 54 kilowatt hours. And when I worked it out, it turned out to be 2.1319 times 10 to the minus 6 grams. And that's just not a nomenclature most of us use in daily use. And so what it works out to be is 1/47 thousandths of a gram. What you have to do is divide 2.1319 into 100,000, and that gives you a denominator with 1 over it. And somebody on Facebook asked me, well, what's that in pounds? And I told him, well, you have to multiply the denominator by 454.5 to convert from grams to pounds. And that gives you some kind of ridiculous figure with a denominator of over 23 million. And that's the reason I chose grams. I chose the smallest measurement unit I had. So at this point, you might all be wondering, well, what's the point of this exercise? There's a couple points. The first one being that E equals mc squared is not something that just applies to nuclear physics. It's all around us in everyday life. If you wind up a child's toy or an alarm clock or something like that, you've added energy to that system. And that system's going to have an increase in mass. But since we're working with the inverse square of the speed of light in this instance, that mass addition or loss, if the system winds down, is very minuscule. And in fact, it's so small that we cannot weigh it with the scales that we have available now, and probably never will. I mean, anything could change the weight. For example, let's say I could weigh my car here, and before and after, I burn off the 54 kilowatt hours. The loss in mass might be canceled out because a mosquito got scorched on my windshield if I was weighing the whole car. Uh, I've been meaning to look it up, find out what a mosquito weighs. But anyway, you get the point. It's just, but mathematically we can deal with this. So there you are. That's number 1 point. And number 2, um, an equivalent gasoline car, let's say we had a gas car approximately the size of a Chevy Bolt here, with it would get let's say 32 miles per gallon, which is a pretty reasonable figure. And 54 kilowatt hours in this car will take me 216 miles. At least that's the rating. And so at 32 miles per gallon, it would take, let's see if I have it here. I've tried to highlight some things. 6.75 gallons of gas, which would weigh a little bit over 42 pounds. So now the gasoline's combined with oxygen in the air and then releases carbon dioxide and water and so forth and air pollution. But that 42 pounds, when you drive that 216 miles, would be gone. It would be dissipated into the air. I mean, it doesn't disappear literally. It just goes someplace else. So now, here's the major point here. To drill for oil, to pump the crude oil out of the ground, and then ship it across the land and the oceans, and then ship it to a refinery, and then refine it into gasoline, and then ship it again and pipeline it and so forth, and finally it'll get to a midway station where it's distributed to gas stations. And then you drive down to the gas station to buy the gas. All that takes a lot of energy to do. There's some estimates that the energy content of the gasoline alone, it takes 2 to 3 times that amount of energy to move that fossil fuel around, process it, and do everything else before you finally get it and use it. So for every gallon of gas, there's 2 or 3 other gallons of gas energy equivalents out there that was in the well-to-wheel inefficiencies of the product. So now, my 1/47,000th of a gram of energy was sent to me over a power line. And the movement of the mass is inconsequential. I mean to say. There are power line losses due to simply resistance. The power lines heat up. And then there's step up and step down transformers at each end and so forth. So there are some losses by the time it gets to me, and there's also losses in the power plants where it's generated, thermal inefficiencies and so forth. But it's nothing compared to a gallon of gas. And by the way, I have solar, so I have solar panels out here 100 feet away, piping me that energy. And there's virtually no losses compared to the losses we're talking about from the power company. And so you could say my car is a fusion car. I also wanted to point out that all the energy that we're using, except for geothermal, essentially is solar power. It is fusion powered. Even the gasoline, or the crude oil, was formed, ages ago from sunlight. And then it was sequestered into the Earth's crust. And we're just digging it up today, or pumping it up today. Only geothermal, which is water heated in the ground from radioactive isotopes in the Earth's crust, which are releasing their heat. is not solar. So anyway, here's the bottom line on this, and I made up a really short table. 1 gallon of gas E, electricity 33,700 watt hours, weighs 1/74 thousandths of a gram. You'll note the fraction gets larger the smaller the amount. At least the denominator gets larger, I mean to say. Gasoline, 33,700 watt hours for a gallon of gas. It weighs 6.3 pounds, or 2,863.35 grams, plus 1/75 thousandths of a gram, is lost. In other words, if you could contain all the products of combustion for the gasoline without the additional oxygen and stuff that comes out of the air, and you could pipe it off somewhere and hold on to it, in theory, all the mass would still be there. But there would be this loss of 1/75 thousandths of a gram. At least that's the way I understand it. I may technically be a little bit fuzzy on some of this, but you get the general picture. So that's all I have for you today. So if you're driving an electric car, enjoy your fusion-powered car, and in an Einsteinian way, you're being very energy efficient. Happy trails, everybody. See you on down the road. Bye-bye.